In this video, I'd like to walk you through from the chapter, or let's call it unit, the Unit 4 review. If you can master each of the questions that's on this review assignment, then I think you're going to be able to do really well on the test. Let's look at this first example. Using rectangle function at the midpoint of the base, estimate the area under the graph using 2 rectangles, and then we'll repeat the question using 4 rectangles. Really important question to start out with. And so I want to spend some time on this, really explaining not just here's the steps, you do this and this, but more than that, I want to take some time to walk you through what it is we're actually doing in this question. What we're at the question again is we're actually trying to find the area under the graph. Notice to do. What we're trying to do is find the area from x equals 1 to x equals 3 under this parabola. So this funny shaped, not a polygon even, but this funny shape that we don't have a formula for, we're trying to find that precise area. We don't have a formula for area of such a funny shape. We have a formula that we can use to find the area of a triangle, of a rectangle, trapezoid, even a circle, but not this funny shape. So here's the process that we can use to find the area of this funny shape. And by this area under the parabola, only going from x equals 1 to x equals 3. So here's how we're doing that problem. The first stage in doing this problem involves finding an estimate. So this problem, use the rectangles to estimate the area, is really in understanding how to find these areas. Eventually, as we get to the chapter 4, or unit 4 rather, we're able to find a precise area by using integrals. We start with that precise area by using this estimate. It's very easy for a 3rd grader or even a 4th grader to find the area of a rectangle. You simply multiply the width times the height. So as you look at these rectangles that you see here in the video, questions asked, they said to find 2 rectangles and that we're using the height as the midpoint of the base. Easy to find these, to draw these 2 rectangles of the base is easy, because if we've got this length going from 1 to 3 and we're dividing it into 2 pieces, then each piece is 1 unit long. 1 unit, 1 unit. So halfway is going to be this 2. So drawing 2 rectangles here is easy, and the width is 1 unit and 1 unit. The height is a little bit more tricky, but not too tricky once you understand what you're. I understand that this could be a very challenging problem and what you're doing. And by the way, if you're paying attention here, Minnie Mouse is here in the video. That might help you with on this assignment, because if you can tell me that Minnie Mouse helped us with problem 1, then that'll alert me that you either cheated by getting that answer from a classmate, or you were in fact watching this video. So how would Minnie Mouse do this problem? She would find the easiest way in the height of each rectangle, and then multiply that height times the width. So the height is going to be value of the function at this point right in the middle, and right in the middle between a 1 and a 2.5. If you're still lagging a little behind with how the width was 1, here's the formula we used. The endpoint was 1 is 2. And then 2 divided by 2 is 1. So what we get here is 3 minus 1 tells us how long this length is. It's 2 units long. And then dividing by 2, because we have 2 rectangles, tells us that each rectangle is 1 width. So we've got the width. To find the height, we're going to, the directions, you could do this using the height of the rectangle if we put the rectangle and the rectangle on its left corner, but the most accurate way is if we use for the height of this rectangle, if we use the height halfway through the rectangle. Halfway through this rectangle, so halfway from point 1 to point 2 is 1.5, because we've got a width of 1 unit and half of 1 unit is 1/2. So 1 plus a half gets us to 1.5. 2 plus a half is going to get 5. F of 1.5, so that just then, and in other words, find 1.5 squared, because this function says square the x. 1.5 squared gives us 2 and 25/100ths. The height of the second rectangle is 2.5. 2.5 squared gives us 6 1/4, or 6.25. So all I've done to find the height of each rectangle is found the midpoint between the 2 edges of the base. So I knew it was a unit. Halfway across would be half a unit. And f of this value of x that's halfway between 1 and 2.5, which is 2.25. So I'm going to move the angle. Comes out to be 2.25 of our second rectangle. The width of 1 times the height of 6.25 gives us 6.25. Estimated area of this yellow thing is approximately 8 5/10 units squared. Now this is not very accurate. I could get a little more accurate or rectangles. So let's try the same problem but with 4 rectangles. If I do the problem using 4 rectangles, now I've got the same length across from x equals 1 to x equals 4 pieces. I've got 3 minus 1 is 2. 2 divided by 4 is a half. So we've got 2 units all the way from 1 to 3. Cutting it into 4 pieces. Each piece is going to be half a unit long. So our first rectangle will start at x equals 1, end at x equals 1 plus a half, or 1.5. And the next rectangle will start at x equals 1.5 and end at x equals 1.5 plus a half, so 2. And the third rectangle will go from x equals 2 to x equals 2.5. And then the fourth will go from x equals 2.5 to x equals 3. Now all I need to do is find width. The width of each rectangle is 1/2. So you see for the area, I'm going to use 1/2. Now I just need to find the height. The height of each rectangle is going to be f of 1.25, f of 1.75, f of 2.25, and f of 2.75. Do you see where those midpoints came from? All I've done is found what's halfway from 1 to 1.5. Half of a half, because the width is a half. So 1/2 of 1/2 is 1/4. So I know that this distance is going to be 25/100ths, or 1/4. So it's 1/4 on each side of the midpoint to give us that whole half. So 1 plus a fourth is 1 1/4, or 1.25. Once we know where the midpoint is, all we do is formula. So 1 1/4 squared, 1 3/4 squared, 2 1/4 squared, 2 3/4 squared, etc. That gives us the heights. So I've tried to pause this video to look at this picture a little bit longer. But we've got our first area, orange area, is the width of 1/2, the height of 1.25 squared, and that area comes up to 0.78125. And so when I have each of the areas calculated here, adding them up, we get an area of 8.625. And that's it. That's all there is to it. So again, the first stage in being able to find this awkward shaped area is to start with being able to recognize that we've got the sum of these estimated rectangles. By the way, there is a shortcut to this arithmetic. Some of you may have already found this, but you notice that we've got this width is the same all the way across. See that what we could do to make this calculation is multiply the 1/2 times the sum of each height. The height of the first rectangle plus the height of the second rectangle plus the height of the third rectangle plus the height of the fourth rectangle will give us the same calculated estimate, 8.625. I hope that that helps you understand how to find the area estimate using rectangles. Next, what we'll move to is seeing that if we made more rectangles, so let's say we did this problem using 8 rectangles, we'd get an even closer estimate. And other than that, we could break it into 16 rectangles and so on. Really what we're going to get to eventually, and this is what the theoretical part of those was doing, was saying that if we made these rectangles smaller and smaller and smaller, eventually what we could say is make them infinitely small and add up the sum. Does that sound familiar? I hope it sounds familiar to you, because in calculus what we do with that is we then say, let's take the limit of the sum as the number of rectangles approaches infinity. So as we increase the number of rectangles from 2 to 4 to 8 to 100 rectangles to 1,000 rectangles, etc., if we use the limit of that sum, we're going to get an even closer approximation and eventually even be able to call it the precise area rather than an approximate area. The definition of the integral is using these Riemann sums, so the sum of each of the areas of each of the rectangles, the sum of each limited, where we use the limit, the number of rectangles is approaching infinity, we eventually start to call that the integration. And that's where the integral comes in. I'm going to stop the video here so that it doesn't long to be able to load, and then we'll resume with problem number 2 in the next video.